So here's several examples of imbalanced dataset occurrences. For example, fraud detection, HIV screening, predicting disk drive failures, okay, and click-through advertising response rates. So all of these tend to have very small percentage of the positive class. Thus, they are rare. Okay, so let's consider, okay, a domain of predicting click-throughs advertising responses. So the expected rate of click-throughs is about 0.09%. This means that a classifier that unconditionally says no, the user won't click has an accuracy of 99.91%. So therefore, in this case, you care far more about the 0.09% of people who click, okay, than the 99.91% who did not. But you care more about which error you make. Okay, so showing an ad to a few people who won't click on it, which are the false positives, okay, isn't so bad. But failing to show an ad to people who would click on it, which is the false negative, is far worse. So this is an example, okay, showing, this shows, you know, the unequal costs and benefits when you are doing a classification. Okay, here's another example. Okay, consider a medical diagnosis domain where a patient is wrongly informed he has cancer. Okay, this we have mentioned earlier. Alright, so okay, if it is a false positive error, the result would likely be that the patient would be given further tests which would eventually disconfirm the initial diagnosis of cancer. This mistake may be expensive but not life-threatening. If, okay, the opposite happens where a patient who has cancer but she is wrongly told she does not, this is a false negative. This would cause missing early detection, hence having far more serious consequences. So these two errors are very different and should have different costs, right? Okay, so the confusion matrix contains frequencies of the 4 different outcomes, which is the true positive, true negative, false positive, and false negative. Okay, so the more precise way to solve the problem of imbalanced data is to use these 4 numbers to calculate the expected cost, or equivalently, you can calculate the expected benefit, right? Because as you can see, by using accuracy as the measurement, okay, and having an imbalanced data set can be misinterpreted, can cause misinterpretation. Okay, so how do you calculate the expected cost? This is the formula. Okay, here the probability of positive and the probability of negatives. Okay, the PP here, these symbols are the probabilities of each class, which is still remember the class priors. Yeah. So this symbol, this one, is a shorthand for the cost of dealing with a positive example. Okay, which is true positive and false negative. Okay, because they are positive examples, though false negative, our algorithm or we ourselves predicted it wrongly. Okay, they are actually positive, but we falsely predict them to be negative. Okay, so cost P here is where you have the probability of true positive multiplied by the benefit of true positive, okay, plus the probability of false negative multiplied by the cost of false negative. Alright? Hence, we have the expected cost here. If we were to elaborate on it, or we shall get this, okay, where you still have the probability of positive, okay, and the probability of negative here, multiplied by the cost of positive, okay, of having positive example and the cost of getting the negative examples over here. Okay, so this is much more precise than accuracy, since it splits apart each of the 4 possibilities for each decision and multiplies it by the corresponding cost or benefit of that decision. Okay, the priors, PP and PN, you can estimate directly from your data. Okay, the 4 probability of true positive, okay, expressions you get from your classifier, specifically from the conversion matrix that comes out of a classifier on a test sample. But the cost function and the benefit functions are extrinsic values that can't be derived from data. They must be quantified from the real-world consequences of the classifier's decisions, right? So these must be estimated based on expert knowledge of the domain. So the cost and benefit functions here can only be estimated by the expert. However, the priors, the PP and the PN, can be derived or can be calculated from the data itself. So let's say we have a case where the positive class is have cancer and the negative class is healthy, no cancer. So the false positives would be where patient is predicted to have cancer but actually does not. And the false negatives would be patient is predicted to not have cancer but actually does. So what is the cost of mispredicting false positive, considering the patient underwent unnecessary treatment, okay, and the expenses that he or she made? And what about the cost of mispredicting false negative, okay? The condition where patient suddenly falls very ill or even died. So these extrinsic costs cannot be derived from the data set, but must be from the real world. All of these costs has to be pre-calculated with the discussion from the domain expert. Hi, so we've gone through 4 phases of the CRISP-DM, and now we come to the evaluation. Okay, the job or the aim of evaluation phase is to evaluate the model. Usually there will be several models that we want to evaluate based on some measurement. The simplest would be accuracy, as we have discussed in the previous video. So now we want to talk about measuring model performance. Every model has its performance that we need to evaluate. So evaluating model performance is specifically about model generalization performance. So you should remember what generalization means or does in data science, which is the ability of an algorithm or a model to be able to correctly predict a data point that it has never seen before or it was not trained with. There are several different performance measures which has been discussed in the previous video. So these are the common ones: accuracy, misclassification, etc. So why do we need to measure the performance of a model? This is similar to a car's stress test. Whenever a manufacturer develops a new car or introduces a new model, it is their responsibility to put that car under a stress test. For example, a crash test or endurance test or gripping, I don't know, tire grip test. Okay, all of this in order to know if the car is capable of doing what it's supposed to and knowing what is its break point. So it goes to say with our model, we want to know how far our model can handle the data set so as to be able to predict correctly. Okay, underneath or underlying all of these tests is a set of parameters. So just like a car, there's a set of parameters, like for example body mass, wheel mass. So whenever the performance is not satisfying, designers and engineers will go back to the parameters and start tweaking. Where is it, what combination of parameters is going to work best with that particular situation. So it's the same with our algorithm or our model. Okay, we want that there are parameters. Different algorithms have different sets of parameters. Therefore, whenever a performance is not up to par, data scientists or data analysts will go back to the parameters and start tweaking and see what can be done, what combination of parameters are there that can be adjusted to produce better performance. Hence, these parameters tweaking can actually lead to overfitting. Overfitting is a condition where we tweaked the parameter of a model to suit the training set very closely to a point that it is not able to generalize well. So if, let's say, you feed a person with, you feed the measurement of a shirt specifically to a person, to a T, okay, what happens is that when that shirt is being used by other people, it will become overfitting, for the first person's body, but not the rest of the other people or other men. But the best fit would be where you can actually use the same shirt size across different sorts of people. Like for example, those free sizes t-shirt or free sizes shirts, so it can range of a wider number of people to wear. So the concept is also similar to when you are doing overfitting for your training set. So you are tweaking your model to suit the training set to a T, so much, fitting it like a glove, so much that when there is a change in the there are new data sets, there are new data points that the model or the algorithm has never seen before, hence it is not able to generalize. So what do? We try to improve accuracy, and yet it's going to, if it's too much, it's going to overfit. So the remedy is to use cross-validation, where you have folds of a data set. There are folds of training set from the overall data set. So imagine that this one line, each line represents the whole data set, okay, and these columns, okay, represent the so-called fold of the data set. So here we have a fold of 5. A fold is basically where you randomly divide the data set into 5 groups. Okay, so if it's 5 folds, so there are 5 groups. Okay, after that, what's done is that one of the folds will be used for training, whereas the rest will be used for testing. Okay, and an iteration of 5, okay, will be conducted where each iteration, during each iteration, the training set will be changed to the next adjacent fold, very much like this. Okay, so for the first run, or for the first run, this fold is the training set, and the rest are used for testing. And then the second run, which is the second row, okay, this fold is now a testing set, and this one is a training set, and the rest is used for testing. So it goes on until to the very end, until the 5th fold, because we have 5 folds here. Okay, what's the benefit of this? The benefit is that you allow the model to train across different folds, or different groups of data, which encompass the entire data set. Alright, so it is more thorough compared to if you just have one iteration, okay, whereby when you have only imagine that you do only the first row. Okay, so the algorithm will learn the data points that are only in this fold, and it will not get to be trained or learned from the rest of the folds or the rest of the data set. So we're not giving a good opportunity for the model to learn as much as possible. Okay, so by doing cross-validation, we allow the algorithm to train with each group of folds that existed inside a data set. So this covers for cross-validation. So the final part of this lecture is on ROC. ROC stands for Receiver Operating Characteristics, okay, where historically it was used as a signal detection on radars, okay, usually in submarines. I might be wrong on the submarine part, but it was used by radar observers. Okay, the whole history, how it comes into data science and data analytics, you can read it on your own. What's important here is that ROC curves is used by data scientists to choose a model. Okay, choose an algorithm, which one is considered better. Alright, so an ROC curve shows a trade-off between true positive rate and false positive rate. The y-axis represents the true positive, and the x-axis represents the false positive. So the area under the ROC curve is a measure of accuracy. Okay, so this whole area would be the accuracy for model A, and this whole area up to this line would be for model 2, not model A, but this side is model 1, and this one is for model 2. Okay, so the tuples, okay, the tuples is ordered in a decreasing order. Okay, the one that is most likely to belong to the positive class appears at the top of the list. Okay, so when we take a look at this, what does it tell? ROC tells you which model has highest true positive rate and lowest false positive rate. So in other words, model 1, okay, is more accurate than model 2. It's better than model 2 because model 1, okay, is closer to this top corner, top left corner, which represents a very high true positive rate but a very low false positive rate. Okay, mind you, the ROC can only be used when the class label is only binary. More than that, it cannot be used. Okay. So this is very useful when you're comparing multiple models for a binary classification problem. So that's all. Thank you.